Thanks for following this third lecture on quantum physics and relativity. In the lectures 1 and 2, we have reached the conclusion that quantum physics and relativity imply each other. You can't have one without the other. The world is at once quantum and relativistic, and the physics describing it should appropriately be called quantum relativistic physics. The quantum relativistic nature of the world has the important implication that the visible material world comes into existence from the invisible, from outside the space and time. And the roles governing the material world, like for instance the conservation of energy, would not function without non-material agency. And even the space-time itself, we have reached this conclusion, even the space-time itself is not merely an arena, but it is an event that comes from outside the space-time. In this lecture, I would like to discuss more in detail how quantum relativistic nature of the world may be related to non-material principles like free will. We consider again the basic experiment of quantum relativistic physics, the single-photon space-like interference experiment. We have here a source, a laser source emitting light, and here a beam splitter, a half silver mirror, so that light can go transmitted or reflected. And here we have mirrors, full mirrors, who reflect the light back the other way. And so light comes here and comes back here and comes back, and arriving again at the beam splitter, they can go this way or can go this way, and here this circulator guides the light so, and here we have two detectors. Alice detector, and here Bob's detector. Here is Charlie, and Charlie can move this mirror in a range so that can change this path, and the optical path length difference of the interferometer. You remember from the other lectures that if these two paths are exactly equal, then Alice gets 100% and Bob 0%. And then when Charlie changed this mobile mirror, then Alice detector will change from 100%. Here is the optical path length that changes when Charlie moves this mirror. Then the counting rate of Alice gets down from 100% to 0% and then increase again, so. And complementarily for Bob, Bob is going from 0% to 100% and then down again. So this is the phenomenon of interference. And this interference means that each of both detectors gets the information about the length of the two paths. The information comes here and the information comes there, but only one of these two detectors clicks, so that each detector knows at which rate he has to count, but in order that only one of them counts, they have to be coordinated. And this coordination, we have seen, is non-local. This coordination works independently of how far away the two detectors are. And so we can conclude that this coordination comes from outside the space and time. So this is the basic experiment of, say, quantum relativistic physics, because the experiment you can work like a Michelson-Morley experiment. You set this path in the direction of the orbital movement of the Earth, and then you can prove by the same experiment also the independence of the velocity of light from the state of movement of the observer. The experiment, as I am describing it here, with single photons, one photon at a time, one photon in each ray, and two detectors. This experiment has not yet been done. The original Michelson-Morley experiment worked with only one detector and not with single photons. So it was considered, and it is considered, a relativistic experiment, but one overlooks that it is also the basic experiment, interference experiment for quantum physics too. I have proposed this experiment to do it as I am explaining to you here, I have proposed to do it in an article submitted in January of this year. But two reviewers commented that there is no need to do it, since the predicted results follow straightforwardly from the results of the original Michelson-Morley experiment in 1887 and the single-photon space-like anti-bunching experiment, which I have proposed in 2010 and has been realized in Geneva in 2012. So, if in this sense the experiment I am describing here can be considered done, according to these reviewers. But I think it would be highly beneficial, highly interesting to really do it in order to provide a definite and unified demonstration of the quantum relativistic nature of the world. To keep the conventional notations of the bits in quantum information, I put 1 if the Alice detector counts, and 0 if Bob detector counts. So, after many runs, we get a sequence of outcomes represented by a bit string. In the output, so if Bob detector counts, we get here, we put a 0 bit, and if Alice detector counts 1. So at the end, we get, as result of the many runs, a sequence 1, 0, 0, 1, 0, 1, 0, 1, 0, 1, 1, and so on. Here, the statistical distribution, say, of the bit 1 in the string depends on the position of this mirror. And the statistical distribution, according to the position, will be between 100% and 0%. So, the rules of standard quantum physics predict only the statistic distribution of the bits, but not the order in which they come out. So, for instance, for a certain position of the mirror, quantum physics can tell us we get 60% of bit 1, and correspondingly here %40 of bit 0. This is what quantum physics predict. But the order in which these bits come out, this quantum physics doesn't predict. The experiment demonstrates this way that at the same time, the quantum non-locality at detection, these two detectors are coordinated, and the independence of the speed of light of the referential frame of the observer. This is what we have said in lectures 1 and 2. Now I would like to stress that this demonstration requires the assumption of the free will on the part of the experimenter. The free will on the part of the experimenter is an axiom of standard quantum physics and of relativity as well. Indeed, if the experimenter's choice of the mirror settings, if Charlie's choice of the mirror settings is predetermined by which path the particle takes after leaving this beam splitter, after leaving BS, the particle comes here. Suppose it takes this path, and then the fact that the particle takes this path would impose nature, would oblige, so to speak, Bob to choose the convenient setting and not to move anything in this path. And reciprocally, if the particle takes this path, then nature would coax Charlie to set the mirror, to change the mirror here accordingly, so that the particle would so travel a path, and Charlie would be coaxed by nature to choose the settings which fit to the choice of the particle. So this would be to say Charlie is not free for choosing the settings of the mirrors. If you make this assumption, then you can get the correlation, the interferences. These interferences, you can get these patterns without any need of this coordination, of the non-local coordination between these two detectors. Simply because the experimenter is obliged by nature to choose the settings which fit to the choices, to which path the particle travels. So you see here that in order to deduce quantum physics, we are implicitly assuming the axiom that Charlie is free in setting the mirror like he wishes. And similarly regarding relativity. For relativity, we have seen it is important to make the experiment, the Michelson-Morley experiment, so that you have one of the paths oriented in the direction of the orbital movement of the Earth, and the other in a vertical direction to this perpendicular direction to the other path, and then you rotate the interferometer. So This is basically the experiment of Michelson-Morley, and demonstrates that by making the experiment, the velocity of light is independent of the state of movement of the observer, of the referential frame of the observer. Well, you could also say here, look, suppose that the source emits the particles, the photons, the particles of light, with different velocities. And so that when the particle enters the path oriented in the direction of the Earth, then if the particle will enter this path, then the source emits this particle with higher velocity. And complementarily, when the source emits a particle which will take this path, then emits the particle with less velocity, with a smaller velocity. If you make this assumption, then you can explain things without any necessity of relativity. Simply by stating the source emits particles with different velocities according to which path the particle takes. Why do we reject this explanation? Because we take for granted that the experimenter is free and could choose to move this mirror and change the length of the path once the photon has entered the interferometer, so that the source cannot know in advance how long the path is. Again, you see, both quantum physics and relativity assume implicitly the freedom of the experimenter. Charlie is free of setting his mirror like he wishes. Is not predetermined in his choices by nature. Once again, the freedom of the experimenter is an axiom for both quantum physics and relativity. And what demonstrates then this experiment is that if you assume the freedom of the experimenter, then this basic quantum relativistic experiment shows that one has to assume free choices on the part of nature as well. That is the amazing thing which is demonstrated by the experiment. As said, in the outcome string here, the order of the bits comes from outside the space-time. Probability 0.5, probability 50%, say, doesn't mean pure randomness in the sense of complete lack of control. The production of any outcome requires non-local coordination between the two detectors. Also, in this other experiment, here and 50% here, and say this is the Alex and then Bob, and then we get the outcome is the 1, 1, 0, 1, 0, 0, 1, 1, 0. 50% 1 and 50% zeros. This is not a complete lack of control. That is, you could say, it is not pure chance, in the sense that for every bit, for instance, if you get here 1, you get here 1 because the other doesn't count. And this means that there is, for each bit you get here, each bit is the result of non-local coordination, of a non-local coordination of the two detectors. If you have, you could say this looks like random, but is a purposeful generation of random outcomes. Any quantum random number generator is actually a purposeful and coordinated generation of randomness. Quantum randomness is a particular form of free will. In this context of quantum non-local coordinations between space-like separated events, which are not time-ordered, when it speaks about expansion of randomness, of the unbelievable randomness, actually, it is better to speak about expansion of free will, and this is known as the free will theory. Although, strictly speaking, it is not that the particles are free, but the agency, the invisible minds coordinating the behavior of the detectors. There is this freedom on the part of nature. Free will is today an axiom of science, as well, you see, on the part of the experimenter, and as a consequence, free will in nature, freedom on the part of nature, and you can accept this, or you can become, or you have to accept this, unless you become faithful of the so-called church of the large Hilbert space, which is, if you wish, like a scientific community which supports many worlds. and similar views, descriptions of the universe. But if you keep to your personal identity and wish to be able of defending your rights, in particular your property rights, then you may be interested in keeping to free wheeler and responsible behavior. This regarding the quantum correlations between space-like separated detectors, coordination between space-like separated detectors. We have seen in lecture 2 that the relativistic local correlations between time-like separated events, the correlations which are time-ordered, for instance, the correlations between the settings of this mirror and the counting rates of the detectors, if Charlie moves his mirror, then the counting rate of this detector and of this detector will change. So Charlie can produce a changing of the rate here, and this action has the action of Charlie has an effect in the counting rate here, which is time order. You can here, if you wish, speak that Charlie moves the mirror, and thereafter here occurs the change of the counting rates. What we have seen in lecture 2 is that also even this correlation, we could say the ordinary relativistic coordinations in our day, you can push on a switch and light the lighting a lamp. These correlations, which are time ordered, we have seen in lecture 2, there's also these correlations actually come from outside the space-time, because between the mirror here and the detector there, actually the space-time is granular, is atomic. So there is no material connection going from the mirror to the detector, from the switch to the lamp. And in this sense, also this kind of correlations, this kind of effects, where we have the feeling that we are causing them, like when I phone to you with my mobile, with my cell phone, then also in this case, in order that the effect can appear, we need this agency coming from outside the space and time. By changing the mirror here, you set a condition to get a change of the counting rate, but the agency which is necessary in order that this change here appears, this agency is also non-material agency. So the visible material comes into existence all the time from the invisible and non-material realm. This has an important consequence. This has the consequence that also these kind of correlations, which in appearance are fully deterministic, actually they are not fully deterministic. And in this sense, Einstein's description of general relativity is being superseded by the results of quantum gravity. So, you see, when we assign to the sunrise tomorrow probability 1, it does not mean that there is an objective feature, a material feature of the world that makes the sun to rise tomorrow. It means that we are practically certain that the sunrise will occur tomorrow, and that's so. Using the wording of a famous Italian mathematician, expert in probability theory, De Finetti, using his wording, one could say that when I say that an event is practically certain, when I evaluate its probability as close to 1, I don't say, nor can I want to say more or less than this, that I am practically certain it will occur. I can say neither more nor less than this. I am practically certain it will occur. The probability 1 or probability 0 assignments of classical physics are in fact judgments, like any other probability assignment. This is the same as assuming that also behind the phenomena described by classical physics, there is a free will which is willed to make them happen with probability close to 1. And therefore, it could also very well make that it does not happen without violating any law of nature. This is normally not the case, but if this would happen, no law of nature is violated by them. If one event from these events we think are certain occur with probability close to 1, if tomorrow the sun doesn't rise, such a phenomenon would not violate any law of nature at all. It would be, if you wish, quite extraordinary, but no violation of the law of nature. So, quantum relativistic physics takes as an axiom the freedom on the part of the experimenter and demonstrates freedom on the part of nature. We could put this in like qualitative equation writing that correlations equal randomness plus coordination from outside space and time. And this coordination from outside space-time, this coordination can be partially local and partially non-local, so that we have two sort of correlations. We have the relativistic, which are time-ordered correlations, and this result from, in this kind of correlations, like for instance the rising of the sun, you have tiny randomness plus large local coordination from outside space and time. This is the correlations we use in everyday life and in the, you wish, governing the classical phenomena. There is no fully deterministic, there are no fully deterministic phenomena. You have also, in every phenomenon, you have a tiny amount of randomness and large amount of local coordination, of time-ordered coordination. But even this comes from outside space-time. And the other equation would be the quantum correlations, which are non-time ordered, these quantum non-time ordered correlations, like this correlation between these two detectors here, these, these correlations result from large randomness plus large local coordination also from outside space-time plus little non-local coordination also from outside space-time. These are the two important statements. In the quantum correlations appearing here, you have large amount of randomness, you have also a large amount of control. You can control the counting rates moving this mirror, and you have also, even in a phenomenon which looks completely random, you have always a little amount of non-local coordination, the coordination between these two detectors, and this coordination comes from outside the space-time, but also the local coordination comes from outside space-time. You remember also, we have explained this in the preceding lectures, that the relativistic correlations lead to energy technologies, like the nuclear technology, but also to the prevailing conventional information technologies like phoning and broadcasting. And the quantum correlations lead to quantum information technologies like cryptography and quantum computing. In conclusion, quantum relativistic physics takes as an axiom the freedom on the part of the experimenter and demonstrates freedom on the part of nature. One should not invoke quantum physics to explain free will, but go the other way around, to assume that free will is an axiom of science. There is no pure randomness in nature. The highest randomness, quantum randomness, is always a combination of free choice and non-local order on the part of nature. And since the real cause of natural phenomena lies outside the space and time, nothing happens in a complete deterministic way. The regularities in nature are not absolute and necessary, but at most events happening with a probability close to 1. Thank you very much for your attention.